All right, so thank you very much for letting me speak here. This is going to be a very different kind of talk, and it's my first talk in this community, so expect something. I don't promise anything. I just want to sell you something. I just want to get right to it. I want to sell you this. If you're hashing, if by any chance you need to perform hashes, that this happens quite a lot in the consensus layer, I want to sell you this library that will hash at the very least, it will hash 20% faster than your current backend without any changes to your code. And if you see here in the bottom, do I have a pointer here? I guess, no, this is just a click. Okay, so if you see here in the bottom, you see that for large trees, this is hashing 4.5 times faster than the common backend. So I just want to sell you this, and since I can sell you in 2 sentences, I'm going to spend most of my talk just telling you what is SHA 256, which is what this library does. But the techniques of this library can be applied to whatever other hashing on the SHA families that I know of. So let me tell you what SHA 256 is. So let's start with this slide. The hashing library is something that generically just takes any message, an arbitrary length message as in a sequence of bits of any length, and it just spits out of that 32 bytes. The digest of this thing is 256 bits. And the procedure to go through those consists of 3 parts. So I'll just go over the 3 parts briefly. The first part is breaking your message into multiples of 64 bytes. So those are the chunks, 512 bits. The second part consists on scheduling words, computing a bunch of double words, which are 4 bytes each. And the third part consists on performing a bunch of rounds, which is just the function that actually does the hashing itself, the function that is not invertible. So here's just a brief description of this slide I just stole from somewhere in the internet. But I want to go in some detail in each one of the 3 parts. So let's start with the easiest one, which is scheduling words. So scheduling words, as you see here, you're given a message. Let's suppose that we've already broken the message in pieces. Each one of them is 64 bytes. So the first thing you do is you compute 48 double words, 4 bytes each. You need 64 in total. The first 16 are your message, are the 64 bytes that you're giving. These are 16 words. And with those 16 words, you can compute the next 16 words. And with those 16 words that you just computed, you can compute the next ones, and the next one, and you computed the 64 that you needed. And the important thing that you need to remember from this slide is that to compute those scheduled words, the only thing that you need is the previous words, nothing else. That means that when you're scheduling words, well, I think the consensus people are starting to come in. Anyways, I've already started, guys. So when you're scheduling words, the important thing is that you don't need to know the previous state of the hashing. You only need to know what were the previous scheduled words. In particular, it only depends on the chunk that you're hashing now, and it doesn't depend on the other chunks that you're going to hash. So if your message consists of 10,000 chunks, you can compute the scheduled words for the 10,000 chunks without caring about how you would hash each one of them, and without caring about the rounds part. So scheduling words only requires the previously scheduled words. So the diagram there is taken out of an Intel paper describing what were 2 new instructions that do this scheduling of 4 words at a time with only 2 instructions. This can be done now on modern CPUs. And this is just a sketch that how diagrammatically you compute 4 words at a time. But it's irrelevant the method that you use to compute those scheduled words. What I want you to remember is that to compute them, you need to know the previous words and nothing else. Rounds, we don't care about what rounds is. We only care that it's a function that is not invertible, that is hard, that is computationally hard to invert. But the important thing that we need to remember is this. We already, we were given the message, we broke it into pieces of 64 bytes that I haven't told you how. We computed those scheduled words that we need, and then what we do is we pass an incoming digest. If it's the very first chunk that you're hashing, we pass a constant digest that the method has. If it's the third chunk, you're gonna pass the hash that the second chunk produced. The point is that you have a status, which is your current hash, and you pass it through this function that takes this status, the hash, the 32 bytes, it takes one of the scheduled words that you computed, and it takes another constant word that the protocol has. So it takes this data, and it produces for you a new hash. So what do you need to remember from this is that you need to have computed at least that scheduled word before passing through the rounds, and you cannot do this in parallel. To pass through the round, you need to have computed already the hash before. So this is something that you cannot do in parallel. Okay, so the padding block. So this is the first part of the three process, which is breaking the message into multiples of 64 bytes. How do you do this? Well, you just break your message into multiple of 64 bytes. You add 1 bit at the very end of the message just to signal this message has ended. So here the message is less than 64 bytes, is 24 bits. These 3 bytes there, A, B, and C. This 1 there is showing that we added that extra bit to show the message has finished. And then you pad with 0 bits up to a multiple of 64 bytes minus 8, because you're going to use the last 8 bytes or 64 bits to encode the length of the whole message. As is there in binary, that's the number 24, which is the actual length of this message. Okay? So this is the procedure to pad your message, which was arbitrary length, into a multiple of 64 bytes. All right. So vectorization, which is the main topic of this talk, is vectorization. So the first thing to notice is that you're not going to beat any of the hashers out there. Every implementation that I've reviewed before I got into this, and I'm not an expert at all on this, I'm come from a completely different subject, but every implementation I've seen is equivalent to Intel's original white paper on this, and it's equivalent to what OpenSSL, for example, does. All of them implement the following. You can compute your scheduled words, as I told you, without knowing what the previously hashed, what the current status of the hashing is. So all of them use vector instructions to compute several words at a time. If your CPU supports 128 bits registers like these ones, and almost every CPU now does, then you're going to compute 4 words at a time, 4 double words at a time. You start with your 16 double words, which is your message, and you can put those 16 double words in only 4 registers. If your computer supports AVX2, it can do arithmetic in registers that are 256 bits, then you're going to compute 8. You're going to use only 2 registers, and you're going to compute 8 words at a time. If your computer supports AVX 512, you're going to compute all of them, the 16 of them at a time. And well, AVX 1024 does not exist yet, but it's already in the books. There's 2 options into computing this. Modern implementations either do this vectorization, or if your CPU implements cryptographic extensions, like what was there in the picture, then they will use 128 bits registers, regardless if your computer has larger registers, because cryptographic extensions can compute 4 words at a time much faster than vectorized computations. But the point I want to make is that this vectorization is there in every current implementation. This is since Intel's white paper. Also, computing the words like this is useful because since you can compute the words and at the same time pass through some rounds, so let's say that you computed the 5th word, then you can pass up to the 5th round. Then you can mix scalar operations with vector operations, and the CPU will perform this in parallel. The CPU has several ports and can take different types of operations at the same time. So you can be computing the 5th round. That is a computation that it has to be done on the scalar part of the CPU because it has to be, it cannot be in parallel. And at the same time, you're computing the sixth word in parallel on vector registers. Okay, so I've covered what is a typical implementation of hashing, and this is the thing to remember from the whole third parts of the talk, is that the hasher signature is this. In either language, it's something like this. It's something that takes an arbitrary length byte slice, and it gives you back 32 bytes, which is the hash. Okay? So it takes an arbitrary length message, and it gives you the digest. And this is something that you're not going to beat. You're not going to implement this better than OpenSSL. No one's going to do. You perhaps can do it for one CPU. You're not going to write an implementation faster than what is already there. However, we use hashing in a very restricted scenario. We use hashing to hash Merkle trees. And Merkle trees are not arbitrary length. Merkle trees are, in the case of the consensus layer, for example, where the nodes are 32 bytes, there's something like this. Each one of these nodes represents 32 bytes, and each parent node has only 2 children, and these 2 children are hashed together. So the 2 children are 64 bytes and concatenated. You hash them, and you get the hash of the parent. You get what goes in the parent. So this is what we hash, typically. And we observe 2 things. Well, actually, the execution layer has something completely different, but still, the same technique is going to apply. What we observe immediately is the following thing. First of all, we're not hashing arbitrary length. We're hashing every single time 64 bytes. And second of all, we can hash this in parallel. You don't need to, you can hash the blue one by knowing the entire left subtree and hash the yellow one completely in parallel in the other side. Of course, you can do this in parallel if you have a CPU if you have 2 CPUs, you can just use 2 threads to hash this, and this is exploited in the consensus layer. I don't know if any other besides Lighthouse uses this, but I want to use this. I want to talk about a different kind of parallelization. You can parallelize this in different threads, but the point I want to make is that you can do this by using vector instructions. So again, this is the typical, this is the one that is in the specs, in the consensus layer specs. This is the implementation. I think this is Vitalik's implementation. This is a flat array approach to having a Merkle tree. I highlighted the line where you're computing the hash of the parent by hashing the 2 children that are concatenated. The top one is different memory layout. This is Proto Lambda's implementation on Remarkable. The point is that it's the same kind of hashing. You take the 2 children and you hash them, and you hash 2 blocks at a time. This is fairly inefficient. This is a Go implementation. This is also Jim's. This is Jim's implementation. This is a production implementation. And then again, the same thing. It's slightly more complicated because it takes into account other things. But the highlighted line is the point where you're hashing, and you hash one node as the hash of the 2 children. And you do this on a loop. For each pair of children, you hash once, you call the hasher, and you get 1 hash. Okay, so I want to tell you what is the right way of hashing a Merkle tree. And it's fairly simple. So there's 2 things that we want to exploit. We want to exploit the fact that this takes an arbitrary byte slice, so this is the layer that you want to hash, and it gives you back a slice of hashes of 32 bytes. So it hashes all of them at the same time. I think I might have gotten this correctly in Rust after several iterations. This would be in Python. We have a library. We have 2 libraries. We have one in Go assembly, and we have one in usual assembly with C bindings. If you are going to use that, let me know, because crypto extensions on ARM is still not implemented. It's going to take like 10 minutes to add this. But this is the signature that the library is going to use if you're using a C bindings. All right, so that's all I want to tell you, and that's it. Sure. Sure.
Sorry we were late, by the way. It was really hard to get in.
I think we started even before the hour was scheduled.
Yeah, cool. So the ability to hash different values in parallel, that doesn't exist in libraries already. Is that right?
It does. So Intel has this library where you give him different messages and it hashes them all at once. So I just copied everything. Nothing here is mine. I just grabbed Intel's implementation and Bitcoin's implementation and put it in a library. The thing with Intel's is that it takes arbitrary length things and it just hashes it and it gives you back just the hashes for all the messages that you give him.
Okay, sure. I'll just repeat that for the sake of the recording. I was just asking if the ability to process multiple different hashes in parallel was already implemented in libraries. That was the question to the answer. So there's two things that you have here, right? One is to like pre-compute the padding block, and then the second is the ability to in parallel process multiple different hash values and then produce multiple different hash values, right?
Right.
And so there are already implementations that do multiple different hash values at once, and you just modified them to deal with the padding block. Is that right?
Yes, and yes. So there are two modifications here. One is the thing that you're going to use the padding block. The padding block has this constant hard-coded, and then there's other modification, which is the fact that you're expected to get a list of 64 bytes chunks, and then you pipeline this. So what this library does is it grabs all of the blocks consecutively in memory. It gets a matrix on the vector registers. It transposes this matrix, and now you have on all of your registers the different messages. So then you can use Intel's machinery to hash those messages in parallel. You you output these hashes, and then you just loop it back. So
okay, cool. So you have, so the result is basically so it's in Go assembly what you have, right?
Sorry?
Your implementation is in Go assembly.
Yeah, so the original implementation was just purely assembly. This is there. It has C bindings, but the C Go overhead is horrible. So it ended up being slower than using the Go implementation, the standard library in Go. So we needed to write a Go assembly library to use ourselves.
Yeah, okay, cool. Well done. Very good, very impressive.
Thanks. Oh, Peter.
Okay, I'll just say. I wonder, after you've done this, have you considered it whether? I don't think this is practical. But it would be interesting if someone tried to design a hash function specifically for hashing Merkle trees, and whether they could do it differently, and how big the savings would be for that if there was like a special hash function for Merkle trees.
I'm sorry, I didn't get this. So
I'll repeat the question. So I was curious, you've shown that there are all these optimizations you have to do to get around the general purpose nature of these general purpose hash functions. Do you think it would be possible to design a hash function that was like a special hash function only for like hashing?
Oh, that's a good question. And I believe, oh, that's a very good question. I need to think. I don't think I can answer this here. I'm not sure if you can do better than the current implementations. Like you can take the sponge type implementations, Sha 3 and company, and you can try to adapt this for this. I don't know. I think, yeah, your question is completely open. It's a very good question. I think we should think about this. So if I understood your question as, can there be a method that is designed for Merkle trees instead of like a generic one? It might be. I don't know.
Oh, sorry to hog the mic. In your implementation, does it, so say there's some really big Merkle trees in the beacon state, right?
Yeah.
Is it the job of the implementation to kind of split that Merkle tree up into smaller subtrees that fit the size of your CPU?
No. So so you're saying if you have this large tree, if it's the job of the implementation in splitting into smaller trees? No. This is completely orthogonal to that. So what you guys are doing in Lighthouse is splitting this into smaller trees, and you send this on different threads to compute them in parallel. This is completely different. You just pass the entire slide. So big trees is the big gain for this. You're going to be at least hashing 4 times faster than the standard library. You just pass the entire slice, like all of the slice that of the bottom slice, and what this thing is going to do is not split into subtrees. What this thing is going to do is grab as many blocks as possible that it can fit in your registers, and then just go to the next chunk and the next chunk and the next chunk and like this. So it doesn't split in subtrees.
Okay, and so you feed it all of the leaves, and then it produces the intermediate leaves.
It produces
and then it produces
next
the root.
layer, and then you just feed it the next layer entirely, and it produces the next one.
Oh yeah, I got you.
So for the state, so you're thinking in the beacon state. For the state, this is incredibly fast, but this is not how we hash the state because we have it in cache typically, and you just have a few nodes that you're changing. So when you hash the dirty trees, the dirty leaves, then well, there's 2 things that happen. So sometimes you have several of them that are consecutive, and then you can be smart and pass this consecutive layer to this hash. Or you can just use whatever you're using now. Just hash 2 blocks at a time. You're not going to get the vectorization impact, but you're going to get at least the 20% of the hardcoding, the padding block.
Yeah, okay, cool. So I guess there's maybe like an argument for maybe it's quite useful for small trees. You don't get a lot from caching.
Yeah, it's not really useful for small trees. You only get the 20% of the padding block.
Yeah, okay.
It's very, very useful on large trees. And here, large means more than 8 blocks. So anything that has depth more than 2, this is already 4 times faster.
Nice, thank you.
Thank you.